All right, electrochemistry involves two main types of processes. The first one is an application of galvanic cells. Now, galvanic cells are simply spontaneous reactions that happen on their own, such as those in a battery. Now, from these cells, we can harvest or make use of the electrons that are given off by the oxidized component of it. The second part are the electrolytic cells, and these are non-spontaneous reactions, and for that sort of thing we require actually an external electron source or a DC power supply, which will drive the reaction. So this allows us, the electrolytic cells allow us to drive electrochemical cells or electrochemical reactions backwards to what we normally see if we just carry out a chemical reaction. Both of these fit into the category that's entitled electrochemical cells. So that's this next topic. The galvanic cell is the one we're going to focus on primarily, also known as a voltaic cell, because it was originally developed by Volta. Although Galvani was the original inventor of it. It consists of an anode, which is the electrode where the oxidation reaction happens. If you watch carefully in a chemical reaction, what happens there is that the anode is eventually starts to become smaller as it dissolves into the solution, because the metal part of it becomes, the atoms become ions as they give off electrons. The cathode is the anode where the reduction occurs, and after a period of time you may see it get bigger and bigger and bigger because the metal ions that are in the solution around it played out onto it as elements. Now, for some elements, when they're not solids at room temperature, we have to use what we call inert electrodes to facilitate the transfer of electrons. And this is a situation where, let's say if we have a situation like when iron 3+ is being reduced to iron 2+ rather than iron metal, or in a situation where we have a gas that is developed as an element, that sort of thing. And so in that case we would end up getting using an inert electrode, so an electrode that will allow us to transfer the electrons, which is a conductive electrode, but won't take part in the reaction. So generally platinum is used as the metal, or perhaps graphite, because most of those materials don't tend to be very reactive and will still facilitate the electron transfer. Also, in a galvanic cell there has to be some way to keep the solutions overall neutral, and so a device that allows for the electron or the ions in solution to transfer their charge from one side of the cell to the other needs to be used. And generally that's either a salt bridge or a porous cup or of some sort that allows for that ion transfer. Now, the electron flow is always from the anode to a cathode, and a good way to remember that is that it's alphabetical order, A to C, right? And this happens through a wire where we connect the electrodes, anode to cathode, from the outside. Quite often some sort of a load is placed in the middle to use up the power that's offered, such as in a battery. We use what's called the standard cell notation to kind of give us a short form for looking at this arrangement. And the cell notation is always written anode on the left, the solution that the anode is in, or the electrolyte, then / the cathode solution / whatever the cathode material is. Okay, and as an example, the zinc copper galvanic cell looks like this: Z, Zn2 plus, Cu2 plus, Cu. Where zinc is the anode and zinc 2 plus is the ions in solution around that zinc anode. On the other side, the copper 2 plus ions are in solution, and the copper is the cathode. And a voltmeter is used to measure the cell potential, or electromotive force, EMF. And this is usually measured in volts. This is a typical arrangement, so a quick sketch of what a galvanic cell looks like, where we have the anode on the left, the cathode on the right. And this is for the reaction of zinc with copper 2 plus ions going to zinc 2 plus ions with copper metal. Okay, we've talked about this reaction a number of times in class. This is what it looks like in an electrochemical cell. This is the more practical side, so the similar arrangement of the previous slide in a practical sense. All right, so oxidation occurs at the anode, which is zinc going to zinc 2 plus, giving off 2 electrons, and reduction occurs at the cathode, where the copper 2 ions grab those electrons and form copper metal. That's the half reactions that we have here. This is another example where we have manganate ions with iron 2 plus forming manganate 2 plus ions with iron 3 plus. So one of the things we need to realize, if we put all these things together in the same container, then the reaction just happens and the electrons transfer directly, and it serves no useful purpose. However, when we separate them like this, then we can make use of these electrons, and this is what we call a galvanic cell or a battery. We can harness this energy if we separate those oxidizing agents and the reducing agents and require the electrons to transfer through a wire, and then that energy can be used to either run a motor, or electric light bulb, that kind of thing, your phones, all that sort of thing. All right. The sustained electron flow can't occur in that first picture. And if we just slip back just for a second here, you'll notice that there's something missing here. That is, what will happen is electrons will flow from the anode here to the cathode. So from anode to cathode. And as a result then, charge builds up on this side. Well, if this becomes a negatively charged electrode, then electrons from this end won't be able to come in this direction because negative charges repel negative charges, right? So essentially the electrons start to move and then stop. So there has to be some way for the charge to be brought back to this side, right? So the ions in solution, if they transfer their charge over to this side, then that keeps everything neutral. So as soon as the electrons flow, a separation of charge occurs, which stops the flow of electrons. All right, how do we fix it? We add a salt bridge. Okay, and it's the job of the salt bridge to balance that charge using an electrolyte of some sort. It connects the two compartments, the anode and the cathode. And here are diagrams of several ways to do that. So there's this green salt bridge here, and there's this porous barrier that can be arranged between two containers. Excuse me. Now, the solution that's in the salt bridge is generally one that is not going to react with either side. So quite often potassium nitrate or some such solution, sometimes potassium sulfate is used as well. Something that isn't going to react with anything with either side of the galvanic cell. The porous disc or cup sometimes solves the problem of having an electrolyte because it simply allows for ions to flow between without the solution itself flowing between. The cell potential is a measure of the pull of the electrons from one side to the other, okay, or the push of the electrons, as it were, from anode to cathode. It's measured in volts, okay, and so essentially the E cell of your little AA batteries that you use for lots of things is 1.5 volts. And this is kind of measured between the components of your anode and the components of your cathode and the electropotential difference. As I said, we use the volt to measure that, and it's equal to 1 joule of work per coulomb of charge transferred. Generally a voltmeter is used for that. As long as we hook it up correctly, it will indicate the electropotential difference of your anode and cathode. Standard reduction potentials are sets of half reactions that are set up so that we can determine what the cell potential is. Now, each potential is kind of an arbitrary value, and so there has to be some sort of a standard. And hydrogen was chosen as the standard electrode to measure all the others against. So the way we do that is we take essentially a test tube. We have a platinum metal wire in there, and then as the hydrogen bubbles up, the electrons jump onto the platinum electrode, and that's how that's set up. Hydrogen electrode is assigned a value of 0, and then everything else is measured against that. Now, the conditions are very specific because these values will change depending on the conditions, the environmental conditions under which you carry out this process. So for gases, if gases are present, they have to be 1 atmosphere. Concentrations are 1.0 molar for solutions, and everything is always at 25 degrees Celsius or 298 Kelvin. We use the degree sign or the naught to indicate the standard conditions. So if you see the little raised 0, it just means that the standard conditions have been met. So E cell or EMF, E cell, these are the different ways you will see it written down. Under standard conditions, those values look like this: the E naught cell, E naught EMF, or E naught cell. Means that those were measured at standard conditions. Now, in university or post-secondary, you will encounter how to determine all of these factors and what to do with the molar concentrations. We're not going to worry about this at this stage. Let's say if we meet standard conditions and we have 1 molar concentrations of everything, then if we use zinc and copper, we are going to get 1.10 volts. The elements that have the most positive reduction potentials are easily reduced, and the elements that have the least positive reduction potentials are easily oxidized. And we can use a reduction potential table, which I will post on D2L shortly. that can be used for that. I will put that in the resources folder. It can be used as an activity series, but it generally has a wider application than just an activity series for predicting reactions or single displacement reactions. The way we calculate the standard cell potential is that we decide which element is oxidized or reduced using the table of reduction potentials. The more positive reduction potential gets to be reduced. We write both sides of the equations, as is in the chart, with their voltages. Reverse the equation that's going to be oxidized, balance the two half reactions, do not multiply the voltage values. Okay, the E0 cell is equal to the E0 oxidation minus the E0 reduction. Simple as that. All right, homework is page 360 and 363. Try those questions and ask questions if you have any at your earliest convenience.